Yeah, I guess that's true. And does this have anything to do with the Schrodinger's cat experiment?
Well, the Schrodinger's cat experiment is the extreme of this, and because it seems so crazy, which is you put a cat. I mean, with an electron, if you're not measuring it, you can't say what state it's in. It's what's called the superposition of states. And if you have a cat in the box, it could be live or dead. And if and there could have been a radioactive decay that proves a bomb that killed the cat, but that's probabilistic. Until you look in, you don't know. So, but if you look in, the cat is either alive or dead. But before you look in, you could say quantum mechanically the cat is in a superposition of a live cat and a dead cat, and then you determine which one when you see it. But that's the extreme version because you're taking a system in which quantum correlations are well, you're correlating a big macroscopic system to the decay of a radioactive atom, which is the radioactive atom is governed by behaves explicitly by the laws of quantum mechanics, and you're making what seems to be a contradiction. But if you think through it carefully, the quantum correlations are such that you never that instantaneously, it's effectively the the cat is always either in a live state or a dead state. It's never in a superposition that can be distinguished as such.
So do you think that it's just the observation is just based on? I mean, I don't. I'm trying. How do you put it? It's like based on hindsight, kind of like you're just looking back at what the There's only two possibilities. You're just looking
Well,
back.
you're applying the laws of quantum mechanics to a macroscopic system,
Right.
and macroscopic systems there's ones in which those quantum correlations, which produce those weird behaviors, get washed out very quickly. So so basically, what happens is that classical systems can be in a superposition, but very quickly they're either in one state or another, and that's why I'm in this room and I'm not outside the room at the same time because I'm very quickly any kind of quantum correlations that might have caused that might have uh, given that kind of strange behavior is washed out so quickly that I behave like a billiard ball
Yeah.
more than
Now
like an electron.
we're talking subatomic levels here. How is there a way you can describe how small this is actually is that we're talking? Can you like put it in context, basically, or
Well, the great thing is that experimental physicists, are now creating macroscopic systems where the weird properties of quantum mechanics are manifest. The simplest one was created in 1911 without knowing it had anything to do with quantum mechanics, and that's superconductivity. If you cool something like mercury down to um, a temperature a few degrees above absolute zero, suddenly all electric resistance disappears. Not gets small, but disappears completely. And if you hook it up to a battery and you get a current flowing and you disconnect the battery, the current will flow forever, forever without resistance. Superconductivity is an amazing phenomenon. We use it all the time nowadays. But and people are searching for what are called high temperature superconductors, where you don't have to cool them down so low to get that weird behavior. But that property is a macroscopic manifestation of laws of quantum mechanics, and you couldn't understand it without quantum mechanics.
so? Now let's just change it up a little bit. There's
Okay.
CERN is colliding particles. What
Mhm.
are they trying to do there? What exactly is the end game here with
The
this?
idea is to build up higher and higher energies because the higher energy you have, the better microscope you have because of the laws of quantum mechanics. So we're trying to basically probe the fundamental structure of matter, and by bombarding, say, protons with higher and higher energy projectiles, what one can explore in some sense the inner structure of the proton and look for new particles and forces, which might help us understand why the forces of nature are what they are and why matter is what it is.
Is this how they figured out about this Higgs boson?
Yeah.
So,
It's because if you smash the particles with enough energy, you can create elementary particles that you wouldn't see otherwise, including the Higgs boson.
and what exactly does that tell us about the universe?
Well, that tells us I wrote a whole book about it called "The Greatest Story Ever Told So Far." But it tells us that in some sense the world around us is an illusion. At a fundamental level, I know, and that'll make the religious people really
It's
happy.
a simulation.
No, it's not a simulation, but it's an illusion. It's of a different sort. I keep going out of focus. I don't know if the camera doesn't like what I'm saying, um,
That's-
but the particles that make us up, electrons, protons, neutrons, have mass, but that's an illusion. At a fundamental scale, they're actually massless. But because it turns out in the early history of the universe, this Higgs field formed throughout the universe, as particles go through it, they experience resistance, and some particles experience more resistance and act like they're heavier, and other particles experience less resistance, like electrons, and act like they're lighter. And some particles, like photons, experience no resistance at all, and they remain massless and still travel at the speed of light. So all of the properties of matter that we see and measure and hold so dear to us are really an accident of the history of the universe. If the Higgs field hadn't relaxed into that configuration it now exists in throughout the universe, then we wouldn't be here. So the fundamental structure of the universe is not at all conducive to our existence. It's just an accident that the Higgs field formed and allowed matter to exist in the form in which we measure it.
And so, if everything's expanding, does that mean it's going to get to a point where it's going to expand so much that it's going to actually affect the reality that we're in? Or is it going to be such a slow change that we don't even notice it?
It's going to keep on. As far as we can tell, the universe is expanding faster and faster, and it's not going to ever stop.
And so is that ever going to affect reality? Like, how is anyone
going to affect reality in the far future, in the sense that all the galaxies that we now see, except the ones we're bound to, our local supercluster galaxies, all of the other galaxies will disappear. They'll eventually be moving away from us faster than light. So in 2 trillion years, all the rest of the galaxies that we can now see in the universe will have disappeared. And beings that exist around stars in our own galaxy 2 trillion years from now will look out and think they live in a universe with a single galaxy, much like we thought we lived in 1925.